Yeah, you can start now. Start sharing.
Yeah, I should share. So, um, writing on the shared screen.
Yes.
Okay. Okay. So now let's begin. So F is finite field of order Q. So I won't be able to read chat messages that pop up. So it's better to just call me. Um,
Sure. Sure. I will.
you
I will remind you. There is something.
right. And G and F reductive group. Then sigma F is Frobenius endomorphism. B0 and F Borel and T0 the maximal Lie split. Torus F torus contained inside the Borel in B0 and W is the absolute Weil group, so it's NGT0 mod T0 the absolute Weil group. So now I'll now recall basics of um, tori about of finite groups. So so we know that at the absolute at the algebraically closed field level, all tori are conjugate. So any torus T is G conjugate to T0. So we can write T is equals to G T0 for some G in G. And this torus T is defined over the base field equivalently if G T0 is sigma F stable, if and only if. So this result proved in Carter's book, sigma F G belongs to the normalizer of the torus. Okay. So then there is this map n in NGT0 to um, uh, so by bar I denote the natural projection in the absolute Weil group, and we have this proposition which is proved in Carter's book that GT0 to G inverse sigma F G bar, this map gives a bijection between GF GF classes of maximal F tori of G and sigma F conjugacy classes of W. So uh, there is a twist. There is a bijection between maximal tori and twisted conjugacy classes of uh, the Weil group, and the map is given in this way. So now let T be G T0 be F torus, and W I should say omega. So omega is G inverse sigma F G bar, and we so our notation is that we say that T is obtained from T0 by twisting with omega. Now let x0 be character lattice of T0, and define conjugation uh, chi0 in x0 maps to G chi0 in x, where x is the character lattice of T, and this conjugation act is defined by G chi0 is that character which sends G T0 to chi0 T0. Then there is a result which there is a lemma in Carter's book, uh, which says that sigma f, this Frobenius, acts on x in the same way as sigma f naught omega inverse acts on x0. Okay, so eh, so the lattice from a given lattice um, by twisting this Frobenius, you obtain uh, the, the Frobenius action on the a different Frobenius action on the lattice, and therefore the F structure on on your different tori, and this exhausts all the tori. So all tori look like this, where you have fixed torus T0, and therefore its character lattice X0, and then you just modify the F structure by this twisting, and thus obtain all the F tori with their F structures. So this is the basic construction of tori. Um, now let F bar be algebraic closure
So in the above definition, G of T,
of
sorry, yeah. So in the above, this GT0 meaning just GT not G inverse, right? The conjugation. In the
yeah G. So yeah, so just GT0
okay,
I should write here GT not G inverse is conjugation.
okay, fine.
So yes, so F bar we take to be the algebraic closure, and let omega the uh, pro group of all complex roots of unity, and right omega prime omega p prime to be those elements, um, those roots of unity which have um, which uh, become one for some n, not divisible by p. And here p is the characteristic of your base field f. Okay, so this is a subgroup of the multiplicative group of complex numbers, and let qp prime is equals to. So in this discussion, what I'm trying to do is uh, uh, identifying with a complex character, which is a representation theoretic object, with a group theoretic object, which will be some uh, character mods, co-invariant of some character. First I need to identify some fields. So write QP prime with a subgroup of the rationals R as S are in integers. P does not divide S. So this is uh, a subgroup of the additive group of rationals. And there is a map R by S maps to the exponential 2 pi I R by S. And this map induces this QP prime by Z to omega P prime. So there was this subgroup of the roots of unity, of which there was omega P prime, and that omega P prime, uh, the um, corresponds to a quotient of the subgroup of rationals. And then the next thing uh, is it. So one can choose an isomorphism, which is QP prime by Z F bar star. So the idea of this isomorphism is not natural. You have to make various choices, but the idea is that F bar star is a union of uh, this increasing cyclic groups. So gamma Ni are cyclic of order Ni, and they are sitting inside each other, and one sitting inside gamma N2, and so on. And then given an R by S, you write it in the form of uh, M by Ni, and R by S maps to gamma Ni to the power Mi. Here here gamma Ni is the generator of this capital gamma Ni. So from elements of Q P prime by Z, you are able to map to uh, the cyclic group, and therefore inside the multiplicative group of the algebraic closure of this field, and therefore you are able to identify QP prime by Z with F star. And in this way, you get an isomorphism. You put together these two isomorphism, you get omega P prime uh, isomorphic to this. Okay. Now note that it requires all these choices of generators so it's not natural. Now fix the isomorphism over. Then um, uh, TF, the rational points of the torus is a finite group of order prime to P. So, uh, so we uh, its characters will land in omega P prime. So we have home T F C star. This will necessarily land inside. So the image will land inside this T F omega P prime, and by the isomorphism that we fix, we get T F F bar star. Okay. So the you have a representation theoretic object complex a character here, and then on the other side we will express it as a group theoretic object. So that requires some work. It's proved in Carter's book, which is home TF C star is isomorphic to X mod sigma minus 1 X. So now this is so you have uh, so I meant to write this F bar star, and therefore um, home TF to C star is isomorphic to X naught sigma F minus 1 X. Now put T in from some conjugation of T naught by an element some element G, and uh, G inverse sigma F G maps to omega. Uh, then in the while group, then we obtain. So by a remark that Frobenius action on the lattice X is given by is comes from the Frobenius action twisted Frobenius action on the lattice X naught. So from that remark, we obtain that uh, this X mod sigma F minus 1 X is isomorphic to X0 mod sigma F omega inverse minus 1 X0. And so we get this corollary that home TF to C star is isomorphic to X0 mod sigma F omega inverse minus 1 X0. Okay. So we have nicely identified uh, the characters of any torus in terms of the original fixed character lattice, the Frobenius, and and the the while group element from which the torus was obtained. Now we write L is equals to L omega is equals to X0 mod sigma F omega inverse minus 1 X0, and omega. Now I'm abusing notation and forgetting the old omega. So points of the Y group of the torus T, which NGTF mod PF. Then uh, there is a lemma which is proved in Carter's book that the Weil group of this torus T, which is obtained by twisting by omega, is the um, twisted centralizer um, of omega is equals to omega. Moreover, the isomorphism of the characters with L is omega equivariant. So all this is part of basic theory in Carter's book on conjugacy classes. And now, if now I'll recall two more facts uh, about the linguistic characters. So if chi is a character, complex character, uh, so character, I'm using some people like to call quasi characters because characters have another meaning in so let chi be a character in uh, position. So that means that it's not fixed by any non-trivial element of the Weil group of T, the efflorational points of the Weil group of T, and T be elliptic. Elliptic means that it's not contained in any proper parabolic subgroup. So if you are given a character in general position of an elliptic torus, then from Dipendra's lecture you have already learned that we obtain a Deligne-Lustig cuspidal pi t comma chi of GF. And in any of those books, like in Michel, you will find this fact that this Deligne-Lustig cuspidal is self-dual if and only if uh, t comma chi is omega conjugate to t comma chi inverse. Okay, so self-duality question um, boils down to uh, uh, properties of this t comma chi, that it should be conjugate omega conjugate to t comma uh, chi inverse, and we will use the term conjugate self-dual pair uh, to denote to give a name to this situation. Okay,
So,
so now
may
yes,
I? So can you just go a
yes,
little bit back, the next,
yes,
just the paragraph before this?
yes,
So what do you mean by this general position of this character? Can you explain it again?
yes. I defined it while I was talking. So I meant, so this means that no non-trivial element of omega fixes the character. So the orbit of chi under omega uh, is the largest possible. So there is no stabilizer of chi in omega on trivial. The
And
stabilizer of chi in omega.
okay, so that's
Huh?
the maximum one. The orbit under this omega action is like the maximal one, some sense, or
Yes. Yes, yes.
okay.
Stabilizer is trivial, yes.
And this elliptic torus mean what? Just I miss. What do you mean by elliptic?
It means that it's not contained in any proper parabolic subgroup of, of the. So it's another way is to see that modulo the center, it is anisotropic.
Okay, okay, okay.
Uh,
Thanks.
yeah. So now there is a special kind of Coxeter torus, elliptic torus called Coxeter torus. So they are obtained from Coxeter elements, and more generally, there is a twisted Coxeter element, and they give rise to this Coxeter tori. So I'll talk about that theory. So twisted Coxeter element. So let omega be product of simple reflections, but not all simple reflections. One coming from each orbit of sigma f in a set of simple roots of g b naught t naught. So we fixed a base root datum gbt naught, and, and in that uh, the 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 Frobenius acts on this, and then you take the orbits, you pick out one element from each orbit, you take uh, the product of simple reflections in any order. What you obtain is called a twisted or sigma f Coxeter element. This element called sigma f Coxeter element. So, for example, if T naught is split, so there is no Galois action, and then the Coxeter element is just the product of all simple reflections. So the basic fact is that W orbit um, of uh, this. So you can form this twisted group W sigma, which means that the W semi-direct with the group generated by sigma. I'm writing sigma for sigma f. Okay. So the W orbit of this, meaning that the twisted sigma twisted orbit of so I'm abusing I'm using mixing words. So when I write omega, I'm calling it sometimes W, but I mean omega because I use W notation elsewhere. So omega, a twisted omega uh, orbit, a twisted omega conjugacy class is independent of the choice of the ordering of the simple roots of the ordering. Okay. And the order of omega sigma, which we denote by h sigma, and simply by h, we drop the notation sigma because sigma we keep fixed. It's called the Coxeter number. It's called the sigma Coxeter number. And sometimes I'll just drop sigma and just call it Coxeter number. And T omega is called the Coxeter torus. And as before, omega is the Weyl group of, of this torus. Then this the good property of Coxeter tora is that its Weyl group is cyclic, and it's generated by omega sigma to the power, where T is the order of sigma, and uh, is of omega is therefore h by T. Okay, so this is the nice property of uh, of Coxeter tori. We know how its Coxeter group looks like, and we know the generator, and we know the cardinality of the Weyl group. So, so this is the background. Now I move on to the
So
proofs.
then, oh, sorry. So this T is equal to this, right? Not the omega, no? Omega is the Weyl group. Uh, so Weyl
Sorry,
group is
what?
cyclic, you mean? So omega is the
Yeah,
Weyl
this
group, right?
yes, this is cyclic. This omega is the Weyl
Okay.
group. I mean, it's the aspirational points of the Weyl group of the torus.
That
So
is
this is a
cyclic. But
cyclic group. Yes.
T omega, that Coxeter torus, that is not cyclic, right? Or
Yeah. So this may or may not be a cyclic group. You mean the aspirational points of T may not be cyclic, but it is sometimes cyclic.
yeah, no, I'm saying this T omega. What do you mean by this T omega? This notation.
So T omega. This is just a notation. Maybe I should. Sorry. Yeah, I should. I meant T is equals to T omega, which is just a notation, which just means that it's GT, where omega is obtained from G inverse sigma
Ah,
F
okay.
G image. Okay, so this is notation. So yeah, so sorry. So T omega doesn't mean co-invariant of T by omega. Sorry. So maybe I drop this notation altogether. So it's I'll just um, so this is the background. So now I move on to the proofs, and proposition. Uh, so I'll state the proposition in some generality, but do the proof in slightly um, less general way. So G is absolutely almost simple. T is the degree of the splitting field of G. T Coxeter torus G H Coxeter element. If H by T is odd, then TF has no self dual characters in general position. So recall our objective uh, for this set of lectures. We want to prove groups we can use the linguistic representations, except that there we have to just prove that uh, an elliptic torus together with the character of the torus in general position exists. So we need to construct such a pair, and i- and uh, and to construct self-dual representations, we um, we have to construct such a pair which is a conjugate self-dual. And in this proposition, we we are taking a Coxeter torus and trying to see whether for which groups Coxeter torus will admit such a pair, and for which groups Coxeter torus will admit a conjugate self-dual pair, and therefore it will produce a conjugate self-dual cuspidal representations. So until now, we have already stated that if H mod T is odd, then there is no hope of getting a conjugate self-dual pair, conjugate self-dual character of the torus. So you have to look elsewhere, produce such a pair, find such a pair, not in the Coxeter torus, but in some other elliptic torus. Okay, and now, uh, moreover, suppose G does not have type 2A2, 2G2, 2, then the following hold. TF has a character in position. So a Coxeter torus, you will always be able to find character in general position. I'm putting out aside some exceptions, which by handle do by hand. Um, if H is not equal to 2, then we can choose such a character to have order L, where L is prime, such that the multiplicative order of Q mod L is H, and if H by T is even, then TF has such a character um, that is also conjugate self dual. Okay, so so you're choosing a Coxeter uh, torus, so it comes equipped with this Coxeter number, the Coxeter element, and T is the splitting field of the group G itself. And from H mod T, parity, we can say whether TF will admit conjugate self-dual characters or not. If H mod T is odd, then torus will not admit a conjugate self-dual character. If H mod T is even, then this torus will admit a conjugate self-dual character, and therefore it will admit. So, and therefore this group will admit conjugate self-dual cuspidal representations. Um, and the middle part is some technicality which we use elsewhere. Um, so, uh, so essentially, this proposition will say that cuspidal representations always exist. Delinguistic cuspidals always exist, and there are two exceptions which are handled elsewhere. Okay, so that's the proposition. Now we begin with the proof of this proposition. So for the proof, I'll assume for simplicity t is equals to 1. So our group is split. Is assumption for this proof, but the proof essentially flows in the same way in the non-split case for this proposition. And remember that we are in the absolutely almost simple case. So let omega coxeter uh, uh, element. So now we don't have to worry about twisted coxeter and all. So it's a coxeter element, meaning that it's product of simple reflections. And sin, and recall that the Frobenius acts by Frobenius looks like this in general as an automorphism of x0, but since your since T0 is split, sigma 0 is 1. So Frobenius acts by Q, the cardinality of uh, uh, the base field. So and the while group is generated by this coxeter element. It's cyclic group generated by coxeter element, and the cardinality of the while group is the coxeter number. And recall L or L group L, which is isomorphic to the complex characters of the rational points of the coxeter torus, is x naught mod sigma omega inverse minus 1 x naught, and sigma acts by q, so it's just x naught q omega inverse minus 1 x naught. So this means that omega acts acts on L by multiplication by q. So q omega inverse acts by 1, which is the same thing as saying that omega acts by q on L. Now suppose H is odd, and so suppose H is odd, and you suppose that there is a conjugate self-dual element uh, in L. So there is a conjugate self-dual character of the torus, of the coxeter torus. In general position. Uh, we do some case. Suppose um, uh, then 2u is equals to 0. Therefore, um, remember that the generator of the while group acts by multiplication by q. Therefore, if q is odd, then uh, qu is equals to q, because q is congruent to 1 mod 2. So 2u is 0. So q is congruent to 1 mod 2. So qu is equals to u. Um, but then u is not in general position, uh, because the action of the while group uh, um, does not have h number of, like it does not, it is stabilizing u, and therefore u is not in general position. And if q is even, then qu is equals to 0. So again, qu powers will not be different. So uh, two different powers of q act in the same way. If you q square u will also be uh, 0, and so u, in other case, u is not in general position. So if u is negative u, then it cannot be in general position. So we now uh, can assume that u is not equal to u. So q to the power alpha u is equals to uh, so q to the power alpha u is equals to negative u for some alpha which is greater than 0 and less than h. Okay, so alpha cannot be 0 because we already ruled out that case. So alpha has to be between 0 and the Coxeter number. But then q to the power 2 alpha u is equals to u, that is q to the power 2 alpha minus 1 is equals to 0. So so h, so some power of q is fixing u. So that power has to be divisible by the Coxeter number. So h divides 2 alpha, since um, u is in general position by assumption. And since 2 alpha is less than 2h, alpha is less than h, so 2 alpha is less than 2h, and h divides 2 alpha. So this means that h um, is equals to 2 alpha. So the only multiple of h which is less than 2 alpha is h itself. So h is 2 alpha, but this contradicts that h is odd. So in this paragraph, we have proved that if the Coxeter number is odd, then there cannot be a conjugate self-dual character in general position. So, so now we move on to do the other parts of the proposition. Now suppose h is equals to 2. So in you can see Our group is absolutely almost simple. So from the tables you can see um, Coxeter number. What is the Coxeter number for which group type? So Coxeter number is 2. Then you are in rank 1 case. Then X has rank 1. So X has to be, so then the group has to be type A1. So it is rank 1. And in that case, L looks like Q plus 1 X. So uh, omega is just one simple reflection, so negative 1. So you get Q plus 1 X. So in this case, uh, so X is just Z. It's rank 1. So in this case, the generator um, of L is conjugate self-dual in general position. Okay. So on the generator, the unique also while group is of order 2 acts by Q, and Q plus 1 is equals to 0. So Q acts by negative 1. So it takes the element generated to its negative. So this covers the case of um, H is equals to 2, Coxeter number 2. So now um, H not equal to 2 and Q comma H not equal to 2 comma 6. So we make this assumption, and then there is a more than 100-year-old result of uh, Birkhoff and Randever, which says that that there exists a prime L such that the order of Q mod L is H. Now let CH double omega inverse denote the characteristic polynomial of the action of omega inverse on X, and let R denote the rank of X0. Then from linear algebra, you know that L is just the determinant um, of uh, the linear transform Q omega inverse Q minus 1. So L is just the um, co image of the transform inverse Q. Um, uh, so therefore its volume is this, and then you can take out Q, so you get Q to the power minus R. R is the rank, so that is omega inverse minus Q inverse, which is the same as Q to the power negative R, and then characteristic polynomial of omega inverse evaluated at Q inverse. Now characteristic, so omega inverse is a finite order um, a linear transform. So from general linear algebra results, you know that this is a product of cyclotomic polynomials, and therefore the sequence of its coefficients is symmetric. From this, it follows that q to the power negative r, uh, this characteristic polynomial evaluated at q inverse is the same as, you can take q to the power negative r inside the polynomial, and so it becomes ch omega inverse q. Uh, Now let phi h denote the uh, or maybe I call this phi d, denote the dth um, cyclotomic polynomial. Okay, so then recall this fact that phi dx d divides h d divides h is x to the power h minus 1, and now uh, L, so h, recall that h um, is the order of q mod L. Okay, mod L. So L divides phi HQ. So if L was dividing some cyclotomic polynomial, phi D, uh, uh, if L divided phi DQ, D smaller than H, D dividing H, then L would divide by this formula, x to the power D minus 1, and so sorry, q to the power D minus 1, and therefore the order of q mod L would be smaller than h, and so uh, that would violate the hypothesis, and so uh, you get that L divides phi HQ. Now, uh, by a result of Springer, so this result is in uh, regular elements in reflection groups paper. It says that it's a bit more general, but for us, this this means that the hth cyclotomic polynomial divides the characteristic polynomial here, and therefore L divides ch omega inverse q. Okay, so what does that mean? So ch, so L, um, cardinality of L was ch omega inverse q, was ch omega inverse q. So L divides the cardinality of L, which means that L has a cyclic subgroup C of order um, L. Now let V be a generator. Um, then, so V is a generator of this cyclic group. Then V is in general position. Why is that? Because V has order L. So all the smaller multiples are all distinct. And so Q, QV, Q square V up to Q to the power HVA are therefore distinct because V has order L. And Q to the power Q has order um, H mod L. So none of the coefficients Q to the power I and Q to the power J are the same if they are less than H. So that in this way you produce a character in general position. Uh, um, now, now suppose, so we have thus produced a character in general position with this exception of, with this hypothesis that Q comma H is not equal to 2 comma 6. Okay. Now suppose H is also even, then since Q has order H model, L does not divide Q to the power H by 2 minus 1, and therefore L divides Q to the power H by 2 plus 1, and thus Q to the power H by 2 uh, acts by -1 on V, and therefore V is conjugate self dual. Okay, so this completes the proof of the proposition when in the split case. Now, in the non-split case, you can do the same thing. So I'll just make some remarks on non. So at this point, are there any questions? If not, then I'll continue. So new remarks on non-split case. So in that case, your sigma is q sigma naught. So it looks like it does not act by um, q, but q times some finite order automorphism sigma naught as odd x, and omega uh, is is generated by this small omega sigma naught to the power t, and the while group has order h mod t, and omega sigma naught uh, acts on or to the power t acts on L by q to the power t. And here, uh, so here we are taking not the absolute Coxeter, but uh, with these changes. Now, but here there is an important difference. Note that H mod T could be odd even if H is even. So this Coxeter number could be even, but what we are interested in is H mod T. That is the order of the generator of the while group. And so there are two uh, um, situations to handle. So remains to handle that q comma h is equals to 2 comma 6, and the case 2 is that h mod t is odd. Okay, so if q comma h is 2 comma 6, then when G is absolutely almost simple, then G is has only very few possibilities. G is A5, C3, D4, G2, 2A2, and 2A3. And all these you do by hand. There are like few lines each to do what to get what we want. So handled by hand. And now I'll write down the table for Coxeter numbers for the twisted types. This is the Coxeter number. So if you have 2an and even, then the Coxeter number is 2n plus 1. 2n odd, then the Coxeter number is 2n. In case of 2dn, it's again 2n, and 2e6, it's 18. So remember that a sigma naught, the degree of the splitting, the order of sigma naught, which is the degree of the splitting field uh, over F, is 2. And that's what this 2 denotes. Okay, so it's 2. So if you divide by 2, you get n plus 1, n, and 9. Each of these are odd. Okay, so you have to look for places elsewhere outside a Coxeter tori. So we have already proved that Coxeter tori will not give you self-dual guys in these places. So uh, in so in so now I'll tell you the E6 case um, where very similar trick works. So in 2E6, H mod T is 9, which is odd. So um, regular is not a term in finite group theory. So let me call this Danilustic cuspidal cell dual. Danilustic cuspidal dual cannot arise from Coxeter tori. Okay, by the proposition that we proved already. So, but we can look for other elliptic tori. So from Springer's work. So Springer studies uh, what I call regular elements, which uh, I won't define or dwell into, but so these are generalizations of Coxeter elements. So this admits regular element W omega sigma naught of order 12, and it associates to an elliptic torus T, and the while group is uh, is is cyclic of order 12, um, by Birkhoff-Randiver result. Result as before, you get that there exists a prime L such that the multiplicative order of Q model is 12, and this uh, so by the definition of L, you see that W sigma naught acts by Q, and W sigma naught square, the group generated by that, is is an index 2 subgroup. So uh, uh, we get our desired result out of Coxeter to right, but we find a Coxeter uh, a, a, a regular element which has very similar properties. That its its while group is cyclic of of the order of order 12, and uh, is generated by this W sigma naught, and W sigma naught acts by Q. So it acts by a scalar, and this. So notice that uh, uh, the while group is not generated by or omega sigma naught square. It omega sigma or naught square um, is an index 2 subgroup. In the Coxeter setting, omega sigma naught square was actually generating the full while group. Here it's generating an index 2 subgroup. So the argument has to be modified a little bit. So by arguments as before, there exists a cyclic C which generated by subgroup of L such that C has cardinality L, and V is in general position with respect to uh, omega sigma naught square. Um, let tau be a generator uh, of omega such that tau square acts by q square. So remember that cyclic groups have this property that there is a unique subgroup of a given order. Uh, so uh, so you tau uh, tau square is tau square, and so it acts by q square. Remember that omega sigma naught acts by q, so omega sigma naught square acts by q square. So we can choose a generator so that tau square acts by q square on C, and let v prime is equals to tau v. So if v prime is not in the group C, then C prime, which is generated by the cyclic group generated by V prime, is a subgroup of L. Again, I mean, it's just a copy moved elsewhere of C of order L. And in this case, it's clear that uh, this omega, uh, uh, in this case, V is in general position. Okay, because uh, you, know, you just easily check that it will move back and forth between the uh, two copies C and C prime, the elements, and so you have this distinct elements. It will keep on moving back and forth, and so V will be the guy in general position with respect to omega. On the other hand, the other possibility is that tau stabilizes C. So C is a finite cyclic group of order L. So its automorphisms are multiplication. Its ort is Z L minus 1. So it's multiplication by integer. So therefore tau acts by multiplication by an integer R, and since tau square acts by q square, so R square is congruent to q square mod L. That is, R is congruent to plus minus q mod L, and so in either case q has order L. So in either case you get um, R has order 12 mod L, and therefore V is in general position with respect to omega, and since R to the power 6 acts by minus 1, so R to the power 6 acts by plus or minus 1. It cannot act by 1 because of the order. So it acts by minus 1 on V. So V is also conjugate self dual. So this completes the proof of E6 case. And so we have gotten rid of, this completes the case of 2E6. So H mod T is can also be odd. H mod T can also be, so from this table, where is the table? From this table, you can see that 2an and 2dn both have h mod t, which have the possibility of being odd, n plus 1 or n. And the n plus 1 or n, these numbers can be odd. You have no control over n. So these are the two remaining cases to be handled. Uh, 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 to find uh, these pairs in general position, and also to find such a pair which is conjugate self-dual. And and so far what we have seen is that we can choose an element whose Weyl group is cyclic, and we can just carry out this trick. And in the case of E6, we could replace Coxeter by an elliptic, by suitably chosen elliptic, and we got cyclic group. This trick ceases to work in the case of this 2an and 2dn. So special unitary and non-split orthogonal case, you just there is no such elliptic element with just the right thing, and so you have to go to more other elliptic tori which have non-cyclic Weyl group. So it will be a product of cyclic Weyl groups. And but the thing that works in our favor is that we have a classification of such tori. So they look like product of Coxeter tori or smaller groups. So we can sort of push this trick further down that road, uh, and prove that these two also uh, admit the required pairs. And case, and then comes a very tedious process of amalgamating groups to build. You know that groups are built out of absolutely almost simple groups, and so this amalgamation process, you have to uh, um, the centers give you a hard time, and you have to do something about it. And then in this way you get the general case for finite reductive group, and for p-adic case you have to lift these results. And there one has a problem that p-adic groups admit inner forms, which is not a problem in finite reductive groups. And so there are many technical difficulties along the way. So some of these things I'll talk about in the next lecture, and at least sketch the outline of the main ideas of the proof. So I'm free to take questions.
Thank you, Manish. Anyone has any question?
So there are also other twisted case, right? So for example, D4 3 D4, and G2 to the table.
3d4 is covered. So 3d4. So I wrote down the proof of in the split case, but in the non-split case, h mod t is even for 3d4.
Oh, that
So
works.
that is covered. Yes, yes. For this proposition,
Uh-huh.
3d4 is covered.
Okay.
So you only have to worry about self-duality when h mod t is odd. Then Coxeter tori will not give you, because that is proved here in the proposition. So then you have to look for elsewhere. And so there were three cases where h mod t is even in the non-split case. There was 2e6, uh, 2an and 2dn.
Okay, these are the only three cases. Okay.
Right, right, right. So yeah.
So
How much?
sorry for D43. What is this Coxeter number? Like H is what? For this is three.
I can look up quickly in
Okay.
this table. So Coxeter number uh, is 10. So it's 12. Uh,
Oh,
you get 12 by 3. So it's 4. So it's even.
okay. Thanks. Yeah.
Very subtle
So,
argument,
so
Manish.
I'll talk about. Yeah, thanks, Deepika. Next lecture I'll talk about the argument that you provided for unitary one.
No, but I am amazed. I think there are a lot of subtleties along the way in this work, and I have not understood various people's names who you quoted. What is Barkov doing?
So this is like more than 100-year-old annals paper. It's
No, but what is it about? I mean, I could not understand what was it about.
so it's
Is
it's
it
it's
possible to
it's
say?
what happens to. Yeah, this is the result more or less that if q this result that if where did I state this? That if q comma h is not equal to 2 comma 6, then
2,6.
q yes, then q has order um, q has order h. There exists a prime L such that q has order h mod L. So it's not a complicated result. It's a simple elementary number theory result.
By Q you mean a prime power? What
Q
is
is the
Q?
cardinality. Yeah, it's the cardinality of the base field, and so it's a prime power.
So given any prime power, you can choose another prime for which it has a desired order.
Right. So I need to look up whether they restrict Q to be a prime power or not. Uh, but but in our case, it doesn't matter. Maybe their result is more general. I have to look up what was the main
How did
statement.
you use this result? How did you use this result? Well, I mean, of course you have used, but can you say without going into details how this has come useful?
So you have to find uh you have this so the main idea is this where is this the main idea is this that the character lattice is the character group of characters is isomorphic to this thing, and so you have to
Okay,
find a
that
cyclic and and the and suppose the torus is suitably chosen so that the while group acts by a scalar. The generator of the while group acts by a scalar. So in this case, it acts by q or q to the power t, depending on split or non-split. So let's think of it as acting by q. So
yeah.
you have to find a large enough cyclic subgroup so that multiples of q are all distinct, and like the up to q to the power h multiples of the generator are all distinct. So if it's a prime number, then of course there are no these are all distinct if it's large enough prime number. So that is the idea.
So it is used to construct a character of the torus of a certain kind.
it is used to construct a large enough cyclic group, and you see that the while group acts on L by multiplication by Q. So so in the cyclic group, you just have so so to produce a regular element implies that the order of Q in that cyclic group is H. And so you have to find a large enough. So you have to find a prime which divides the cardinality of L. Then you will be able to find a cyclic group, and the prime should be such that the order of Q is H mod that prime. So this exhausts large number of cases, the Coxeter ones.
You are still in the Coxeter case.
In the Coxeter case, and then what we do is whenever Coxeter does not work, we look for an element so, which does the Coxeter-like behavior. So there is only one case where it does the Coxeter-like behavior, the 2E6 case, where the while group is cyclic. And then remain the two cases to handle, which is this unitary and non-split orthogonal. There you have product of Coxeters of smaller rank groups. So you can sort of push this trick further. So the while group is not cyclic, but it's product of cyclic groups. So you can still push this trick, and that is the idea. And then there is this this amalgamation part, how the centers interact.
But I don't understand. You can use the adjoint group, no?
Yeah, so you have to prove lemmas about isogenies, but
No, but since you are doing results for general reductive groups, in particular, you are constructing a self-dual self-dual Deligne-Lustig representation, Cuspidal.
yes, right. For adjoint group, yeah. So you can embed the character lattice in the sim the one of simply connected one, yes. And then decomposes into product of
Adjoint
absolute.
looks better.
So adjoint, there X embeds in the thing, and so then you have to prove that. So adjoint, I must have discarded at some point. It was a candidate to work with and then left with isogenies, but you will see.
I see. Adjoint is not good enough.
So no, it's not.
So the restriction mapping.
It is used.
Yeah, I see that the representation may become reducible. So there is a mapping from G to
right,
and it may be irreducible on adjoint, but restricted to G, it may become reducible. Okay. So
right. So I'll talk about these details and the so I don't have enough time in the lectures to talk about many details, but this I think I'll try to cover the proof that you supplied for unitary part, and then I don't know how much time I'll have for amalgamation part, and then I want to talk about versatility in lifting in the p-adic case, and there is also this issue with inner forms, which is absent here.
Right.
So putting together you get this.
Yeah. No. So there are many subtleties along the way.
Yeah, it's proof is complicated.
Although eventually the theorem is quite pretty, but it has to go through some case by case analysis.
Yes, yes. It will be spectacular to make it shorter than that. It's only 19 pages, so it's not very long, but yeah,
No,
you have to handle 2 or 3 cases separately. And then for very small fields, you have to handle some cases, but to reduce your hypothesis. Uh, so you have to handle some small groups, and eventually we cannot handle some small groups when the field is very small. So we just put them aside in the hypothesis that the field is not very, very small, of cardinality typically larger than 5, to get the uniform statement.
all these details must be in your paper, no?
Yes, yes,
Good. So I think I will say goodbye to you, Manish. I
yes.
am still in my office and I need to go home. So good seeing
Uh-huh.
you. A wonderful lecture.
Yes,
Wonderful lecture.
thanks, Iped.
Maybe we will talk on some other occasion.
Yes, yes, of course.
Okay.
Anytime.
Yeah, yeah. Bye. Bye.
Bye.